Right now, 642 light-years away, a star is dying. Not gradually fading over billions of years, but preparing for one of the most violent events the universe can produce. And we're watching it happen in real time. Betelgeuse. The name alone carries weight in astronomy circles. This red supergiant marks the shoulder of Orion, visible to anyone who looks up on a winter night. For thousands of years, it glowed steadily. Then in late 2019, something changed. The star dimmed, dramatically. Astronomers scrambled to their instruments, because they knew what this might mean. A supernova. An explosion so powerful it would briefly outshine every other star in our galaxy combined. Visible during the day, casting shadows at night. A celestial event that happens maybe once per century in a galaxy like ours, and we might be about to witness it. But here's what makes this genuinely unsettling. We have no idea when. Could be tonight. Could be 100,000 years from now. The light we see left Betelgeuse in the 1380s, when the Ming Dynasty was just beginning. If it exploded tomorrow, it actually happened during the Renaissance, and we're only now receiving the news. The star itself is almost incomprehensible in scale. Place it where our sun sits, and its surface would extend past the orbit of Jupiter. Every second, Betelgeuse burns through mass equivalent to Earth's moon. It's so large that its outer atmosphere is actually cooler than the deeper layers we can detect, creating convection cells the size of our entire solar system. Scientists discovered something else recently. The dimming in 2019 wasn't just a fluke. Betelgeuse had ejected a massive chunk of its own surface into space. A piece of star, flung outward, temporarily blocking our view. The sheer violence required to tear that much material away from a supergiant's gravity suggests internal processes we're only beginning to understand. Stellar physics gives us the framework. Betelgeuse is fusing heavier and heavier elements in its core. Hydrogen is long gone. Helium, exhausted. Now it's burning carbon, oxygen, silicon. Each stage happens faster than the last. Silicon fusion, the final step before catastrophe, takes about 1 day. 1 day between normalcy and detonation. The core contracts under its own gravity. Temperatures spike. Pressures mount. Eventually, even silicon can't hold back the collapse. In less than a second, the core implodes, then rebounds. The shock wave tears through millions of kilometers of stellar material. What took millions of years to build destroys itself in hours. That's the supernova. But the story doesn't end with the explosion. What remains is stranger. The core, compressed beyond anything we experience in everyday physics, becomes either a neutron star or a black hole. In Betelgeuse's case, given its mass, we're likely looking at a black hole. a point in space where gravity is so extreme that not even light escapes. The entire mass of a star, compressed into a region smaller than a city. Meanwhile, the outer layers race outward at roughly 10% the speed of light. This expanding shell carries every element the star forged over its lifetime. Iron, gold, uranium, everything heavier than helium. These materials will eventually seed new star systems, new planets, possibly new life. Every atom in your body heavier than hydrogen was created in a star that died before our sun was born. The supernova remnant becomes a nebula. Glowing debris spreading across light years, enriching the interstellar medium. Within these clouds, gravity begins pulling material together again. The cycle continues. Now consider what this means for us. At 642 light-years, Betelgeuse is close. Not dangerously close, but close enough to matter. When it goes, we'll see effects beyond just a bright light in the sky. The explosion releases more than visible light. Gamma rays, X-rays, ultraviolet radiation, all pour out in the initial burst. Earth's atmosphere will absorb most of this, but satellites might not fare as well. Communication systems could experience disruptions. GPS might lose accuracy. Nothing catastrophic, but noticeable. Then there's the neutrino flux. These ghostly particles barely interact with matter, but a supernova produces them in staggering numbers. Trillions will pass through your body every second for weeks. Detectors worldwide will register the surge, giving astronomers unprecedented data about the explosion's mechanics. The visible brightness is what captures imagination, though. At peak, Betelgeuse will reach apparent magnitude -12, roughly as bright as a half-moon. You'll see it during the day. At night, it'll cast noticeable shadows. For weeks, possibly months, our sky will have two moons, one white, one red. Cultures throughout history have marked supernovae. The 1006 event was recorded on three continents. The 1054 explosion created the Crab Nebula and appeared in Chinese and Middle Eastern texts. Native Americans left pictographs depicting it. These weren't just scientific observations but events that shaped mythology and worldview. What happens to us when Betelgeuse goes? Nothing physically dangerous, but something profound psychologically. We'll have front-row seats to cosmic violence on a scale that makes our largest nuclear weapons look like firecrackers. It'll be a reminder, visible every night, that the universe operates on timescales and energy scales that dwarf human concerns. Astronomers are preparing. Telescopes across every wavelength stand ready. When the light arrives, we'll have perhaps hours of warning from neutrino detectors before the visible light reaches us. Every major observatory will pivot to Orion. This will be the most studied astronomical event in human history. The data will be invaluable. We've never observed a supernova this close with modern instruments. Our models of stellar evolution, nuclear physics, even general relativity, will face their most rigorous test. Whatever we think we know about how massive stars die, Betelgeuse will either confirm it or force us back to the drawing board. There's also the question of what we'll find afterward. The neutron star or black hole left behind will be young, hot, energetic. We might detect pulsar emissions, jets of material shooting from the poles at near light speed. The nebula itself will be a laboratory for studying shock physics, dust formation, and chemical enrichment of space. But I mentioned earlier that the timing is uncertain. Let's dig into why that's so frustrating. Stellar models tell us Betelgeuse is near the end. Its behavior, the dimming events, the mass loss, all point to a star in its final stages. But final stages, for a supergiant, might mean tomorrow or 100,000 years from now. The physics becomes chaotic. Small changes in core conditions produce wildly different outcomes. We're essentially trying to predict the exact moment a Jenga tower falls. We know it's unstable. We can see pieces missing. But that final trigger, the precise instant when structural integrity fails completely, that's incredibly difficult to forecast. The 2019 dimming gave us hope for better predictions. If we could understand what caused it, maybe we could identify pre-supernova signatures. The research that followed revealed the surface ejection, but also showed us how much we still don't know. Betelgeuse is variable on multiple timescales. It pulsates. It sheds mass irregularly. Separating normal variability from end-stage behavior is like diagnosing a patient whose symptoms keep changing. Some astronomers think we're seeing the final centuries. Others argue we might have tens of thousands of years left. The uncertainty stems from how we measure stellar evolution. We can't watch a single star age. We observe millions of stars at different life stages and piece together the sequence. It's like understanding human aging by taking snapshots of random people and arranging them by apparent age. You'll get the general progression right, but predicting any individual's remaining lifespan becomes much harder. Recent observations added another wrinkle. Betelgeuse might have a companion star. If true, the dynamics change completely. Binary interactions can trigger supernovae earlier than expected, or delay them, or create entirely different outcomes. We thought we understood this star, and then realized we might have been looking at a system, not a singleton. The implications stretch beyond academic curiosity. Understanding supernovae helps us understand galactic evolution, element formation, even cosmology. Type Ia supernovae, a different class from what Betelgeuse will produce, serve as distance markers across the universe. They helped us discover that cosmic expansion is accelerating, leading to the concept of dark energy. Getting the physics right matters for our entire picture of how the universe works. And there's something else. Something that connects directly to why this particular star captures our attention beyond the scientific interest. Human timescales collide with cosmic timescales in strange ways. Betelgeuse might explode while you're reading this. Or it might wait until our civilization is dust. From the universe's perspective, there's no difference. A few thousand years either way is a rounding error. But for us, the difference between witnessing this event and having it remain theoretical is everything. We stand at a unique moment. We had the technology to study a nearby supernova in detail, but we lack the ability to predict when it'll happen. Our instruments are ready. Our models are sophisticated. But nature keeps its schedule, indifferent to our preparations. There's a philosophical tension here that's worth examining. We study the universe by observing light that left its source years, centuries, or millennia ago. When we look at Betelgeuse, we're seeing photons that began their journey around 650 years ago, give or take. The star might have already exploded. The shockwave could be racing toward us right now, and we wouldn't know until the light arrives. This isn't speculation. It's the fundamental constraint of information traveling at light speed. We're always looking backward in time. That delay creates an odd psychological state. Astronomers monitoring Betelgeuse know that the supernova they're waiting to observe might have already happened during the Middle Ages. The light carrying that information could arrive next week, or next century. There's no way to check. No faster-than-light telephone line to call and ask if the star is still there. We wait, instruments ready, knowing that the event we're preparing for might be a historical fact we just haven't learned about yet. Let's shift perspective for a moment. What would it actually look like from Earth? The first indication would come from neutrinos. These ghostly particles barely interact with matter, which means they stream out from the core collapse essentially unimpeded. Neutrino detectors around the world, designed primarily for particle physics research, would register a sudden spike. These facilities are networked specifically for this purpose. When one detector sees an anomalous burst, it alerts the others. If multiple detectors confirm simultaneously, astronomers worldwide get an automated notification. Supernova imminent. Look up. The neutrino warning would give us maybe a few hours head start. Possibly a day. Then the light would arrive. Not gradually. Supernovae brighten dramatically, exponentially. Within hours, Betelgeuse would go from roughly magnitude 0 to potentially magnitude -11 or 12. For context, the full moon sits at magnitude -13. We're talking about a single point of light nearly as bright as the moon, visible in broad daylight. Orion would be unrecognizable. The constellation would have a second sun blazing where the hunter's shoulder used to be. That peak brightness would last weeks, maybe months, then a slow decline over years. But even after fading, Betelgeuse would remain visible to the naked eye for potentially decades. The expanding debris cloud would eventually form a nebula, visible through telescopes for thousands of years. This isn't a brief light show. It's a multi-generational transformation of our night sky. The scientific return would be staggering. Every telescope on Earth and in orbit would immediately swing toward Orion. We'd capture the light curve with unprecedented detail, tracking how brightness changes second by second. Spectroscopy would reveal the composition of ejected material, testing our models of nucleosynthesis. Did the supernova produce the expected ratios of elements? Are there surprises in the chemical signature? X-ray and gamma-ray observations would probe the shock wave physics. Radio telescopes would track the expanding shell as it plows into surrounding material. And then there's the neutrino data itself. These particles carry information about the core collapse that light cannot provide. Light gets trapped, bounced around, delayed by the dense stellar material. Neutrinos escape immediately, carrying direct information about nuclear reactions in the collapsing core. Detecting them in large numbers would let us peer into physics we can't access any other way. The temperature, the density, the exact sequence of nuclear processes, all encoded in the neutrino spectrum and timing. Previous nearby supernovae were observed with far more primitive instruments. Supernova 1987A in the Large Magellanic Cloud, while spectacular, occurred before we had modern detector networks. We caught neutrinos, which was revolutionary, but with limited sensitivity. We got optical observations, but without the resolution and wavelength coverage we have now. Betelgeuse would be the first nearby supernova in the era of space telescopes, gravitational wave detectors, and coordinated global observation networks. The data haul would rewrite textbooks. But there's something else happening alongside the scientific opportunity: cultural impact. Betelgeuse going supernova would be the most dramatic astronomical event in human history, at least in recorded history. The 1006 supernova was brighter, but occurred before the scientific revolution. Ancient observers recorded it with awe but without understanding. The 1054 supernova created the Crab Nebula. Chinese astronomers documented it. Indigenous peoples across the Americas incorporated it into their traditions. But again, no scientific apparatus to study it properly. A supernova in Orion would reach everyone. You can't miss Orion. It's visible from almost everywhere on Earth. Every culture recognizes it. Suddenly, that familiar pattern would change. Children would grow up with a sky that looks different from the one their parents knew. Photographers would capture the light illuminating landscapes. Artists would respond. Writers would find metaphors. The supernova would become part of human culture in ways we can't fully predict. There's precedent for celestial events capturing public imagination, though nothing quite at this scale. Comet Hale-Bopp in 1997 became a cultural phenomenon. People who never looked up started watching the skies. But Hale-Bopp was a visitor, here and gone. Betelgeuse would be a permanent change. The supernova would fade, but the sky would remain altered. We'd live with the consequence, the glowing remnant, for the rest of our species' existence. Now, let's address something often glossed over in popular discussions. Could this actually be dangerous? The short answer is no, but the reasoning matters. Supernovae release tremendous energy, including gamma rays. At close range, within a few dozen light years, a supernova could potentially damage a planet's atmosphere. The gamma rays would interact with atmospheric molecules, creating nitrogen oxides that deplete ozone. Without ozone protection, surface life would face increased ultraviolet radiation from the star. Betelgeuse is too far away for this to be a concern. The inverse square law is brutal. Intensity drops with the square of distance. At 650 light-years, the gamma-ray flux reaching Earth would be negligible. Detectable, certainly. Scientifically valuable, absolutely. But not hazardous. We'd receive more radiation from eating a banana than from Betelgeuse's supernova. This isn't speculation. We can calculate these things precisely. The physics is well understood. Some articles sensationalize this, either through misunderstanding or for clicks. You'll see headlines about killer stars or cosmic threats. It's nonsense. Real astronomers aren't concerned about danger. They're excited about the scientific opportunity. The distinction matters because public misconceptions about astronomy can undermine science communication. We need people to understand that space, while genuinely dangerous in many ways, doesn't threaten us with random nearby supernovae. The galaxy isn't that hostile. What could genuinely affect us is more subtle. The supernova's effect on the solar wind dynamics, perhaps. Earth's magnetosphere protects us from charged particles streaming from the sun. A supernova would add a temporary burst of high-energy particles to the cosmic ray background. Our magnetosphere would handle it, but satellites might experience slightly elevated radiation. Nothing catastrophic. Maybe some temporary communication disruptions. GPS might lose accuracy. ISS would need to monitor exposure levels. Astronauts might need to shelter in more shielded areas during peak flux. Again, manageable. Not apocalyptic. The real challenge would be observation coordination. Every major observatory would want time on every major telescope. Conflicts would arise. Who gets priority? How do you balance spectroscopic observations against photometric monitoring against polarimetry against imaging? Normally, telescope time is allocated months or years in advance through competitive proposals. A supernova would trigger directors' discretionary time at every facility, overriding scheduled observations. Some astronomers would be thrilled. Others, whose carefully planned observations get bumped, less so. There's also the amateur astronomy community to consider. Betelgeuse is bright enough that backyard telescopes could contribute real data. In fact, amateur observations might prove crucial for continuous monitoring. Professional telescopes can't watch one target constantly. They need to split time between multiple objects, multiple projects. Amateurs, coordinating globally, could maintain near-continuous coverage. We saw this work effectively with other transient events. The amateur community has become genuinely valuable for time-domain astronomy. Social media would transform the experience compared to historical supernovae. Real-time updates, images, data, all shared instantly worldwide. Scientists could communicate findings directly to public audiences. Misinformation would also spread rapidly, of course. Distinguishing signal from noise would be challenging. But overall, the transparency would be unprecedented. You'd be able to follow the supernova's evolution as it happens, explained by experts, discussed by millions. Educational impact deserves mention. A visible supernova would provide a teaching moment like no other. Students could observe with their own eyes a phenomenon they'd only read about. Teachers could connect textbook physics to something happening overhead. The abstract becomes concrete kai ban ko the chi te veo no. Bao tung qua ha kasi ze dung kak kuok trian lam. Kak kung thien van se kap not kak bui trin dien qua ho. Su kien nai se trian kam hung cho mot the he kak na thien van hoc. Jong nu chuang trin apollo de trian kam hung cho kak the he na qua hoc va ky su truok day. But we keep circling back to the central frustration. When? We have this extraordinary opportunity ahead of us, maybe. Or maybe not for 100,000 years. The uncertainty undermines planning. Observatories can't keep resources on standby indefinitely. Research teams can't maintain readiness for decades. Funding agencies want timelines. Yet the universe doesn't provide them. Betelgeuse will explode on its own schedule, indifferent to our preparations or impatience. We've built the instruments. We've developed the theory. We've coordinated the networks. Now we wait. And waiting, in astronomy, often defines the job more than the observations themselves. What we do know is that Betelgeuse isn't behaving like other red supergiants we've studied. Most stars in this phase show relatively predictable brightness variations. Long-period pulsations, yes. But within expected ranges. Betelgeuse keeps surprising us. The great dimming of 2019 to 2020 caught everyone off guard. The star's brightness dropped to around 40% of normal. Some astronomers genuinely wondered if we were watching the prelude to explosion. Spectroscopic analysis eventually revealed the truth. Betelgeuse had ejected material that condensed into dust, temporarily blocking our view. The star itself hadn't actually dimmed that dramatically. We were seeing an obscuration event. But that explanation raises its own questions. Why did Betelgeuse eject that much material at that particular time? Red supergiants lose mass continuously through stellar winds. The rate varies, certainly, but that particular ejection seemed unusually vigorous. Was it a surface convection event? Some models suggest that massive convection cells in red supergiant envelopes can bring hot material to the surface, creating localized bright spots. When those regions rotate out of view, the star appears dimmer. Combine that with dust formation and you get dramatic brightness changes. Except we're not entirely certain that's what happened. Alternative models exist. Maybe the dimming involved magnetic activity. Betelgeuse does have a magnetic field, though measuring it precisely is difficult. Could magnetic loops trap material, then release it suddenly? Solar flares operate on this principle, scaled way down. A stellar version might produce the observed effects. We're speculating, though. The truth is we saw something unprecedented and we're still working out what it meant. This uncertainty pervades supernova prediction. We're trying to forecast an event we've never actually witnessed up close in real time with modern instruments. SN 1987A happened in a large Magellanic Cloud, 168,000 light-years away. Close enough to study extensively, far enough that resolution was limited. Betelgeuse at 550 light-years would give us detail we've never had before. But only if it explodes while we're ready. The waiting game has psychological dimensions worth examining. Astronomers dedicate careers to studying objects that might not do anything interesting during their professional lifetime. You could spend 30 years developing expertise in supernova physics and never witness the one event that would define your field. That's the gamble. Some researchers pivot to other topics, hedging their bets. Others commit fully, accepting that the universe operates on timescales indifferent to human careers. There's nobility in that commitment. Also frustration. Imagine explaining to funding committees why your telescope time should go toward monitoring a star that probably won't explode this year. Or next year. Or the year after that. Competing proposals promise guaranteed results. Yours offers a possibility. Funding agencies generally prefer certainty. Yet Betelgeuse observations continue. Not constantly, but regularly. The star remains on monitoring lists. Photometry gets collected. Spectra get recorded. Data accumulates slowly, building a baseline against which any future changes will be measured. That baseline has value regardless of whether Betelgeuse explodes soon. We're learning about red supergiant behavior in unprecedented detail. The variations, the mass loss, the atmospheric dynamics, all of it contributes to stellar evolution models. When the next red supergiant explodes somewhere else, we'll understand it better because of Betelgeuse. The question of what we'd actually see during the explosion deserves more detailed exploration. The initial brightening would be gradual, probably over hours. Neutrinos would arrive first, traveling essentially at light speed and passing through matter almost without interaction. Neutrino observatories around the world maintain constant vigilance for the characteristic burst signature. They'd detect it before anyone saw anything visually. Minutes to hours later, the shock wave from the core collapse reaches the stellar surface. The star's outer layers begin exploding outward. This is when brightness starts increasing dramatically. Over the course of a day or so, Betelgeuse would brighten from magnitude 0.5 to perhaps magnitude -11 or -12. Roughly the brightness of a half moon, concentrated in a single point. You could read by it at night. Easily. During the day, it would be visible to the naked eye, a bright star hanging in daylight sky. The color would shift too. Betelgeuse appears reddish now because its surface temperature is relatively cool for a star, around 3,500 Kelvin. During the supernova, the expanding material heats up. The color would shift toward white, maybe even slightly blue. The expanding debris would be glowing from the energy of the explosion itself, not from fusion anymore. Peak brightness would last weeks, maybe a couple months. Then gradual fading over years. But even after fading below naked eye visibility, the supernova remnant would remain a target for telescopes for centuries. The expanding shell of debris, glowing in various wavelengths, would evolve constantly. Radio observations would track the shock wave as it plows through surrounding space. X-ray telescopes would study the hot interior regions. Infrared would pierce any dust that forms. Optical telescopes would monitor the overall structure. Each wavelength reveals different physics. The remnant would become a laboratory for studying extreme conditions we can't replicate on Earth. Nuclear physics, particle acceleration, shock wave dynamics, all happening in real time at scales we can actually resolve. Most supernova remnants we study are ancient, their explosions having occurred thousands of years ago. A fresh one at Betelgeuse's distance would be transformative. Consider the scientific papers that would emerge. Hundreds in the first year alone. Thousands over the following decade. Every subfield of astronomy would find something relevant. Stellar evolution theorists would refine their models of red supergiant death. Galactic chemical evolution researchers would study how the explosion enriches surrounding space with heavy elements. Particle physicists would analyze neutrino data to constrain physics beyond the standard model. Cosmologists would use it to calibrate distance measurements, since Type II supernovae serve as standardizable candles under certain conditions. The interdisciplinary reach would extend beyond astronomy. Geologists would look for isotopic signatures in ice cores or sediment layers, markers of cosmic ray exposure from the supernova. Historians might correlate the event with cultural responses, studying how different societies interpret and record the phenomenon. Artists would create works inspired by it. Musicians might compose pieces. The cultural impact would ripple outward in ways we can't predict. But there's a darker consideration that occasionally surfaces. What if we're wrong about the safety? Not about the distance, that's measured reliably, but about the radiation effects. Current models say we're safe. Models have been wrong before. The ozone layer might be more vulnerable than we think. Or the magnetosphere less protective. Unlikely, yes. Our understanding of these systems is solid. But certainty in science always comes with error bars. The responsible position is acknowledging what we don't know while being clear about what we do. We're confident Earth is safe from catastrophic effects. Confident, not absolutely certain. That distinction matters. Scientists who claim absolute certainty lose credibility when exceptions emerge. Better to be honest about uncertainty while explaining why we consider the risk negligible. Public communication requires that balance. Climate scientists face this challenge constantly. How do you convey high confidence without claiming perfection? How do you acknowledge uncertainty without undermining the message? With Betelgeuse, the stakes are lower because we're not asking anyone to change behavior. No policy decisions hinge on supernova predictions. But the communication challenge remains. Media coverage of Betelgeuse tends toward sensationalism. Headlines scream about stars exploding near Earth, implying danger where none exists. Scientists issue corrections. The cycle repeats. Each brightening fluctuation triggers another round. After a while, public attention drifts. The boy who cried wolf effect takes hold. When the supernova actually happens, will people care? Or will they assume it's another false alarm? Maintaining public interest over uncertain timelines is nearly impossible. The first few times Betelgeuse dims or brightens unusually, media covers it extensively. By the 10th time, it's old news. Editors reject the story. The public assumes nothing real is happening. Then one day, it actually explodes, and everyone's surprised despite decades of warnings. This dynamic frustrates science communicators. How do you keep people informed without exhausting their attention? Some researchers have stopped doing media interviews about Betelgeuse entirely. The questions are always the same. Is it exploding now? When will it explode? What will we see? The answers never satisfy because they involve uncertainty. Journalists want definitive statements. Scientists offer probabilities and caveats. The disconnect is fundamental. Yet when the explosion happens, those same researchers will be flooded with interview requests. Everyone will want expert commentary. The preparation happening now, the monitoring, the theoretical work, the instrument development, all of it will suddenly become urgent and newsworthy. The irony is that the real scientific value lies in the preparation, not the event itself. The supernova will be spectacular, certainly. But the decades of work leading up to it, building our understanding of stellar evolution, developing detection capabilities, training new generations of astronomers, that's where the lasting impact lives. Betelgeuse will eventually teach us something we can't predict. Every major astronomical event does. When gravitational waves were first detected, nobody expected the precision with which we could measure neutron star mergers. The technology worked better than anticipated. The data revealed phenomena theorists hadn't considered. Supernova 1987A taught us about neutrino physics in ways no one foresaw. The neutrino burst arrived hours before the light, exactly as predicted. But the detailed measurements refined our understanding of particle interactions inside collapsing stars. Models improved. New questions emerged. Betelgeuse will do the same, just in different ways. Perhaps we'll discover unexpected asymmetries in the explosion. Maybe the dust production will challenge our models of element formation. The neutrino signal might contain surprises. We won't know until it happens. This uncertainty is what makes the event scientifically valuable. If we could predict everything perfectly, there'd be no point in observing. Science advances through surprises, through data that doesn't quite match expectations. Those mismatches force us to reconsider assumptions, revise theories, build better models. The process is iterative and endless. Consider the stellar evolution models we use. They're sophisticated, incorporating decades of research. But they're still approximations. Real stars are messier than equations suggest. Convection patterns inside Betelgeuse are turbulent and chaotic. Our models smooth them out, treating them statistically. That works for predictions but misses fine details. When Betelgeuse explodes, we'll see whether those details mattered. Did the asymmetric convection create asymmetric explosions? Did rotation play a bigger role than we thought? These questions have answers we can't access until the event occurs. Some researchers are already planning follow-up studies for decades after the supernova. The expanding remnant will be visible for centuries. Its evolution will test our understanding of how supernova remnants interact with surrounding material. Currently, we study old remnants from supernovae that exploded centuries or millennia ago. With Betelgeuse, we'll watch one develop from the beginning. That temporal coverage is rare and valuable. The remnant will sweep up surrounding gas, heating it, compressing it, possibly triggering new star formation. These processes occur in every supernova remnant. But observing them in real time, with modern instruments, will provide unprecedented detail. Computer simulations can be compared directly to observations. Models will improve. Future predictions will become more accurate. There's also the question of what Betelgeuse leaves behind. Supernovae from stars this massive typically produce neutron stars. But some create black holes instead. The boundary between these outcomes isn't perfectly understood. It depends on the star's exact mass, its composition, how much mass it lost before exploding, and details of the collapse process. Current estimates suggest Betelgeuse might be right on that boundary. If it produces a neutron star, we'll have a new pulsar to study. If it forms a black hole, that's equally interesting. Either way, the remnant will teach us about the final moments of massive stellar cores. Neutron stars are extreme physics laboratories. Densities exceed atomic nuclei. Magnetic fields reach unimaginable strengths. Matter behaves in ways we can't reproduce on Earth. Every new neutron star adds to our understanding. Black holes are equally fascinating but harder to study directly. We'd infer its presence through effects on surrounding material. Gas falling toward it would heat up, emitting X-rays. Over time, the black hole might accrete enough material to become visible through those emissions. But that takes years or decades. Immediate detection would rely on gravitational wave observatories. If Betelgeuse's core collapse is asymmetric enough, it might produce detectable gravitational waves. Current detectors probably aren't sensitive enough at that distance. But future observatories might be. LIGO and Virgo are upgrading. New detectors are being built. By the time Betelgeuse explodes, we might have the capability to detect its gravitational wave signature. That would be extraordinary. We've never detected gravitational waves from a supernova. The asymmetry required is substantial. Most supernovae probably don't produce detectable signals. But if Betelgeuse does, it would open an entirely new window into core collapse physics. We'd learn about the exact moment the core fails, how matter falls inward, how the bounce generates the explosion. These are processes hidden inside the star, invisible to traditional telescopes. Gravitational waves carry information directly from the core. They're not blocked by overlying material. This makes them uniquely valuable for studying supernova interiors. Neutrinos serve a similar purpose. They interact so weakly that they escape the collapsing core almost immediately. The neutrino burst from Betelgeuse will arrive before the light, just like with 1987A. But this time, our neutrino detectors are far more sophisticated. IceCube in Antarctica can detect thousands of neutrinos if predictions hold. Super Kamiokande in Japan will see them too. Multiple detectors worldwide will triangulate the signal, pinning down the exact timing and direction. That coordination will happen automatically once the first detector alerts the network. Within seconds, astronomers globally will know Betelgeuse has exploded. They'll point every available telescope at it. The race will be on to capture the earliest moments. Amateur astronomers will contribute significantly. Professional telescopes can't cover the entire sky simultaneously. But thousands of amateur observers can. The first visible light detection might come from someone's backyard telescope. That's how supernovae are often discovered. Automated surveys catch many now, but amateurs still find them regularly. With Betelgeuse, the amateur community will be watching closely. Many have already planned their observation strategies. They know what equipment to use, what filters to apply, how to record data properly. When the moment comes, they'll be ready. This democratization of astronomy is relatively recent. Decades ago, meaningful contributions required access to major observatories. Now, affordable equipment can capture scientifically valuable data. Amateurs discovered comets, tracked asteroids, monitored variable stars. They've become essential parts of the astronomical community. Betelgeuse's supernova will showcase this collaboration beautifully. Professional astronomers will coordinate with amateur networks. Data will flow in from every continent. The global effort will be unprecedented in scale. And it needs to be. The first hours and days are crucial. That's when the shock wave breaks through the star's surface. That's when we see the initial flash, the rapid brightening, the spectrum changing minute by minute. These early moments constrain models of the explosion mechanism. Missing them means losing irreplaceable information. Automated systems will help. Robotic telescopes can respond within seconds of an alert. They'll begin collecting data before humans even know the supernova started. But human judgment matters too. Deciding which observations to prioritize, which instruments to use, how to adapt to unexpected developments. These decisions require expertise and intuition. The combination of automated systems and human oversight will maximize the scientific return. We're not just waiting passively. Preparations continue constantly. Observation plans are refined. Software is updated. Detector calibrations are checked. Communication networks are tested. When Betelgeuse explodes, everything needs to work perfectly. There's no second chance. Some might wonder why we invest so much effort into one star. The answer is that Betelgeuse represents an entire class of objects. What we learn applies to red supergiants everywhere. These stars are crucial for galactic chemical evolution. They produce and distribute heavy elements. Understanding their life cycles and death throes helps us understand galaxies themselves. Every galaxy contains stars like Betelgeuse. Most are too distant to study individually. But Betelgeuse is close enough for detailed observation. It's a proxy for countless others. The investment in studying it pays dividends across multiple fields. Beyond the science, there's something profound about witnessing cosmic events in human timescales. Most astronomical processes unfold over millions or billions of years. We see only snapshots. Stellar evolution happens too slowly to watch. But supernovae are different. They're fast. A human lifetime might encompass the entire visible phase. That connection between cosmic and human time makes supernovae special. We can experience them, not just study them abstractly. When Betelgeuse explodes, people worldwide will look up and see something genuinely new in the sky. That shared experience will be remarkable. Different cultures will interpret it differently. Some will see it as an omen. Others as a spectacle. Scientists will see it as data. All perspectives are valid. The night sky belongs to everyone. Throughout history, bright astronomical events have left marks on human culture. Supernovae recorded by ancient astronomers influenced art and mythology. The 1054 supernova that created the Crab Nebula was documented across multiple civilizations. Betelgeuse will be brighter and closer. Its cultural impact could be substantial. Modern astronomers might create detailed records, but they'll also capture something previous generations couldn't: real-time public engagement. Social media will light up instantly. Images will spread globally within minutes. The scientific community will share observations openly, faster than ever before. This transparency changes how discoveries unfold. Previous supernovae occurred before the Internet age. News traveled through traditional channels, slowly. Professional papers took months or years to publish. By contrast, Betelgeuse's explosion will be documented second by second online. Live streams will show telescopes tracking it. Data will be posted immediately. The entire process becomes visible. Some worry this openness might spread misinformation. Fair concern. Spectacular events attract wild speculation. We'll see claims about danger, about cosmic rays, about effects on Earth. Most will be nonsense. The challenge is separating signal from noise. Education becomes critical. Astronomical organizations are dechuan by kak chien dike thon tin som som. Kai siu tan tin zara, thon tin chin zak kan ko san nai lap tuc. En hung jai tik ro ran v en hung gi dang zara, no ko nia la gi, en hung wan noi him now kong tun tai. Su min bok fu dao lam jiam su hom lon vanam lan. Because there will be questions. Lots of them. Can the supernova harm us? No, the distance is far too great. Will it affect our weather? Not measurably. Could radiation reach Earth? Negligible amounts, harmless. These answers need to be ready, accessible, repeated often. The physics is straightforward but counterintuitive. 600 light-years sounds close astronomically. In human terms, it's incomprehensibly distant. Light from the explosion travels for 6 centuries before reaching us. Any dangerous radiation disperses across that vast gulf. By the time it arrives, it's weaker than cosmic rays we experience constantly. Neutrinos will arrive first, actually. They pass through matter easily, so they escape the collapsing core before light does. Detectors worldwide will register a sudden burst of neutrinos. This signal arrives hours before the visible brightening. It's the earliest warning possible. Neutrino detectors are already monitoring constantly. They're designed to catch exactly this scenario. When Betelgeuse collapses, detectors will see the neutrino pulse and send alerts automatically. Astronomers will have precious hours to prepare before the light reaches us. Those hours matter immensely,